Up to now, the grammars we've used have been provided for you. But if you are building a new programming language, you have to design those rules yourself. You probably know that an assignment statement needs an identifier, an equal sign, an expression, and a semicolon. But computers don't understand English descriptions. We have to convert that human intent into exact production rules. Designing a compiler requires you to shift your mindset and think purely in strict, formal structural patterns. The first rule of grammar design is to never start with grammar symbols. Instead, start by identifying the language constructs you want to support, like an assignment statement. Look at these assignment snippets. To build a grammar rule, we extract the abstract patterns shared across them: an identifier, an equal sign, an expression, and a semicolon. That isolated pattern then morphs directly into a formal production rule. Statement produces ID equals EXPR semicolon. Basic grammar design is simply the act of taking these repeating code patterns and locking them into formal templates. The second rule of grammar design is to break large structures down into smaller, reusable parts. A rigid rule, like an identifier equals 3 identifiers with math, rejects anything else. It fails on A plus B. The solution is modular design. Breaking this massive rule apart lets a top-level statement call an expression module to handle its own logic. By separating the grammar into connecting components, the parser can handle infinite code variations without breaking. Let's build out that expression module to handle recursive addition. An expression recursively expands to generate strings like ID plus ID. But adding multiplication directly into this flat structure creates ambiguity. In the split screen, the flat grammar reads an equation 2 conflicting ways. The compiler might calculate addition first, violating basic math. To solve this, we create a hierarchy: addition at the top expression layer, multiplication in the middle term layer, and operands at the bottom. Pushing multiplication lower in the grammar forces it lower in the parse tree. Evaluated bottom-up, multiplication mathematically happens first. Establishing this vertical hierarchy is the universal mechanism compiler designers use to enforce exact operational precedence. Now, apply this modular thinking to control flow. Take a few seconds to look at the structure of an if statement and try to write the formal production rule yourself. The rule defines a statement as f, a parenthesis, an expression, a closing parenthesis, and another statement. We now combine the assignment rule, control loops, and layered arithmetic into one cohesive block. This tiny grammar successfully processes many code snippets. A perfect grammar achieves these 3 things. It generates all valid strings, rejects invalid strings, and structurally enforces precedence without ambiguity. Now that we have written a working grammar, we have to define exactly where the work gets done inside the compiler. Look at this single mathematical expression. We have to determine who actually recognizes the individual numbers and who recognizes the overarching mathematical structure. We will map the exact boundary between lexical analysis and syntax analysis in the next lesson.